Final project number 2, Cross-Maltese Algebra Geometric Model. I'm Vincent Joaquin Mamawag from BSED Math 3B. Final project number 2, explore each subgroup and draw a lattice diagram relating the different subgroups. Subgroups. If a subset H of a group G is closed under the binary operation G, and if H with the induced operation from G is itself a group, then H is a subgroup of G. We shall let H is less than or equal to G, or G is greater than or equal to H. Denote that H is a subgroup of G, and H is less than G or G is greater than H shall mean H is less than or equal to G but H is equal to G. If G is a group, then the subgroup consisting of G itself is the improper subgroup of G. All other subgroups are proper subgroups. The subgroup E is the trivial group of G. All other subgroups are non-trivial. These are the improper subgroups. We have the G equal to the set of elements of A, L, G, E, B, R, U, H, 1, 2, 3, 4, 5, 6, 7, 8. We have the trivial subgroups, which is A. And we have here the proper subgroups, which is the G sub 2. Consists of element A, L, G, E, B, R, U, H. And to check if it is a group, it is closed under binary operation star. It is associative. There is an identity element A which is also found in a set, and there is an inverse element for each element. So A inverse is equal to A, L inverse is equal to H, G inverse is equal to U, E inverse is equal to R, B inverse is equal to B, R inverse is equal to E, U inverse is equal to G, H inverse is equal to L. So checking for its associativity. If we rotate it into 180 degrees and interchange the rows and columns, we can see that it is same as the original. Therefore, it is associative. G sub 3 G sub 3 is equal to the set of element A, G, B, U, 1, 3, 5, 7. And to check if it is a group, first, it is closed under binary operation. Second, it is associative. There is identity element A which is also found in this set, and there is an inverse element for each element. So A inverse is equal to A, G inverse is equal to U, V inverse is equal to 7, U inverse is equal to G, 1 inverse is equal to 1, 3 inverse is equal to 3, 5 inverse is equal to 5, 7 inverse is equal to 7. Now, checking for its associativity. If we rotate it into 180 degrees and interchange rows and columns, we can see that it is same as the original. Therefore, it is unassociative. Next, G sub 4 is equal to the set of element A, G, B, U, 2, 4, 6, 8. A, to check if it is closed under binary operation star. Next, it is associative. And also, there is an identity element A which is also found in the set. And last, there is an inverse element for each element. A inverse is equal to 1, G inverse is equal to U, B inverse is equal to B, U inverse is equal to G, 2 inverse is equal to 2, 4 inverse is equal to 4, 6 inverse is equal to 6, 8 inverse is equal to 8. Now, checking for its associativity. Rotating it to 180 degrees and interchange rows, we can see that it is same as the original. Therefore, it is associative. Same from the previous subgroups, G sub 5 is also a subgroup since its proven that it is closed under binary operation, it is associative, and there is an identity element A which is also found in the set, and there is an inverse element for each element. Same as in G sub 6, G sub 7, G sub 8, G sub 9 and G sub 10, G sub 11, G sub 12, G sub 13, G sub 14, G sub 15, G sub 16, G sub 17, G sub 18, and that's the last subgroup. So these are all the subgroups. We have the improper subgroups, trivial subgroups, and proper subgroups. And now this is the lattice diagram.